Hello and welcome to this revision session for AQA Physics Paper 2 on the topic of electric fields. So in today's revision session we're going to be looking at how to answer examination questions on A-Level Physics Paper 2, in particular the topic of electrical fields. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions on electrical fields, assess our understanding on A-Level Physics topic electrical fields, and understand what topics of the electrical field module we need to improve upon for A-Level Physics. So how should you prepare for revising in this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and to show your full working out. Whilst on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for your A-Level Physics examinations? Well, the first step is to learn the key facts, learn the knowledge. So use revision guides, class workbook, student preparation notes and the textbook to learn the key ideas of the course. You may wish to make mind maps or to write out notes yourself. Second step is to test yourself. So use the Caboodle e-learning platform, the Seneca e-learning platform, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then the third step is to practice. Practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to help answer examination questions and to mark your own work. Now you may wish to download your own examination past paper to do this. So the three steps of learning the key facts, then testing yourself, and then practicing exam style questions will help you to revise for your A-Level Physics examinations. Now in this revision session you'll find three types of questions. The first one is a general check question. So these are basic questions designed to probe your understanding of the key concepts of a topic. The second one is a checkpoint. So these are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. Then finally you've got your assessment point questions, which are past paper exam questions which mimic the type of questions found in public examinations. So with that, let's now have a look at some questions on electrical fields. So the first question says, sketch the electrical field lines near a positive charge of plus Q, sketch the electrical field lines near a charge of negative Q, and then sketch the electrical field lines near a larger negative point charge. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can be able to sketch electrical field lines correctly. So this first one, because it's a point charge, all the electrical field lines will meet at that point charge. Now you'll also note that it's going to be a radial field because it's a point charge. And then finally as well, the arrows should be pointing outwards because they will follow the field lines follow the direction a positively charged particle would take at that point in the field. So because positive repels positive, the field lines would be outwards because the positive charge would move outwards. Now for this next one, it's going to be the same pattern except the field lines are pointing inwards now because your negative point charge would attract your positive charge, which is the test in this instance, so therefore they'll be pointing inwards. Now if you've got a larger negative point charge, well, it tells you you've got a stronger force of attraction, so it's still an arrow pointing inwards, but to show field strength in this context you would have to have your field lines closer together because the density of the field line indicates the field strength, so you'd have more field lines per unit area. The next question says, draw the electrical fields between the following charged objects. You've got 5 different pictures there. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to remember that the field lines will always go from a positive to a negative because that's the direction in which the objects will move, because that's the direction the test charge would move in. So you'll see here that you've got parallel lines in the plate because between two charged plates you get a parallel field lines, so you get a uniform field between two parallel plates. They'll also curve slightly outwards once you pass the plate boundaries. The next one, again, you've got the field lines going from the positive to the negative like so. Again, again here you've got the radial field going outwards, meeting that plate there to go through like that. Again, the opposite direction in terms of the arrows for the negative charge, because you obviously got because obviously the field lines will move in the direction that the test positive charge will be in. And then finally here you've got your radial field all pointing outwards because it is a positive charge. The next question says, 2-point charges of 2 nanocoulombs are separated by a distance of 1 centimetre. Calculate the electrostatic force experienced by each charge. Then, without detailed calculation, state and explain how your answer to the first question would change when the same charge is separated by 3 centimetres. Now, the electrical field at a distance of 5 centimetres from the centre of a charged dome is 3 times 10 to the 4 newtons per coulomb. Calculate the charge on the dome, and then calculate the force between a helium nucleus and a gold nucleus at a distance of 2 times 10 to the minus 14 meters. A gold nucleus has 79 protons and a helium nucleus has 2 protons. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is using Coulomb's law, which is F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Again, this equation is given to you in your equation sheet, and epsilon 0 is a constant given to you on your equation sheet as well. You pop in all the numbers. Now remember, nano means 10 to the minus 9, and then remember we'll turn centimeters into meters, so we 0.010, and remember it's r squared. So you pop in the values and it's 3.6 times 10 to the minus 4 newtons. Now you'll see from this equation F is directly proportional to 1 over r squared. So when r increases by a factor of 3, when distance of or separation increases by a factor of 3, well, then the force will decrease by a factor of 3 squared, which is 9. So you divide your previous answer by 9, so it's 4 times 10 to the minus 5 newtons. The next one, again, we're using the equation to work it through. Now, in this case, we're actually using the electrical field strength equation, which is electrical field strength is equal to Q over 4 pi epsilon 0 r squared, which is the electrical field strength for a radial field, which it will be. It's a charged dome. So you can work it through, make Q the subject, pop in all the values. Remember, centimeters turns into meters. It's a squared for r as well, so it's 8.3 times 10 to the minus 9 coulombs. Then this last one, we are using Coulomb's law again. F equals Q1 Q2 over 4 pi epsilon 0 r squared. Pop in all the numbers. Remember, the proton has a charge of 1.6 times 10 to the minus 19 coulombs. That's a bit of revision from the particles topic. Pop in all the values. Remember, it's r squared, and we get 91 newtons as our force between them. The next question says, calculate the electrostatic force and then the gravitational force of attraction between 2 protons at a separation of 2 femtometers inside a nucleus. Compare the magnitudes of the 2 forces and whether they're attractive or repulsive. And then in Ernest Rutherford's alpha particle scattering experiment, helium nuclei were fired at a gold nucleus. Calculate the repulsive force between the helium nucleus and a gold nucleus when they've got a separation of 50 femtometers. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, we're using the Coulomb's law for the electrostatic force, and we're using the gravitational force. We're using the Newton's law of gravitation for the gravitational force. So we use F equals Q1 Q2 over 4 pi epsilon 0 r squared. Pop in all the values. Remember that you are given the charges there of both of them, okay, and you can work that through. It should be 1.6 times 10 to the minus 19. Okay, so they will work through. Okay, and you can work it out like that, and you get 57 newtons. Now again, remember, because they are both the same charge, there'll be repulsive force. You do the same for the gravitational force, which is F equals G m1 m2 over r squared. Pop in all the values. Again, you're given the masses of the protons and neutrons on the equation sheet. You can get that through to be 4.7 times 10 to the minus 35 newtons, and gravity is always an attractive force. So you can do so what you can do is you can find the ratio between the two of them, because one is under the ratio of 10 to the 1, because it's in the tens orders of magnitude. One is 10 to the minus 35, so therefore the electrostatic force is 10 to the 36 times larger than the gravitational force. Again, in this next one, we're using Coulomb's law, popping in all the values, working it through, and we get our answer to be 15 newtons out. The next question says, an electrical engineering technician has been asked to carry out an investigation into 2 charged particles. The technician has carried out some investigation and has found that the charge on the first particle is measured as 0.3 coulombs, which has a repellent force of 172 newtons on a second particle. The second particle is 1.2 meters away from the first particle. Calculate the charge on the second particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one again we're using Coulomb's law, so we're saying F equals Q1 Q2 over 4 pi epsilon 0 r squared. Now we're going to use that equation and rearrange it to work out Q2, the charge on the second particle. So you can say Q2 is equal to F times by 4 pi epsilon 0 r squared over Q1. Pop in all the values, then work it through, and we get 9.17 times 10 to minus 8 coulombs. Now it's important to note that this is a positive charge. How do we know that? Well, because it is producing a repelling force with another positively charged particle, so therefore it itself must be positively charged. The next question says, for the point charges of plus 25 microcoulombs and plus 100 microcoulombs separated by a distance of 60 millimeters, calculate the magnitude of forces exerted on the plus 25 microcoulomb charge by the 100 microcoulomb charge. Then 2 point charges plus 4.0 nanocoulombs and minus 80 nanocoulombs are placed 80 millimeters apart. Calculate the magnitude of the force exerted on the plus 4 nanocoulombs by the minus 8 nanocoulombs charge. State the nature of the force. And then 2 point charges are placed a distance apart. The force in each charge at this distance is 40 newtons. The distance between the charges is doubled. Determine the new force that each charge experiences. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we're using Coulomb's law. F equals Q1 Q2 over 4 pi epsilon 0 r squared. You can pop in all the values and you can work it through in case you know that we're going to be turning our microcoulombs into coulombs. Pop in all the values through and we get our answer out to be 5.5 times 10 to the 4 newtons. Again, we're using Coulomb's law here to work it through, and we work it all out by popping in the numbers. We know nanocoulombs means 10 to the minus 9, and we're doing r squared. Remember, millimeters turns into meters. So that's 10 to the minus 3. So we get our answer out to be minus 4.5 times 10 to the minus 5 newtons. Now it's an important idea to note that when you've got a negative force, in this particular instance it's an attractive force, and if you get a positive force in this instance it's a repulsive force. So because it's a negative value, you know the nature of the force is attractive. Now in this next one we know the relationship that F is directly proportional to 1 over r squared. So therefore if the distance doubles, the force will decrease by a factor of 2 squared, so it's 1 over 4. So therefore if it was 40 newtons, it'll now be 10 newtons because the force has decreased by a factor of 4. The next question says 2 parallel plates are 4 centimeters apart and have a potential difference of 2.5 kilovolts between them. Calculate the electrical field strength between the plates. A small piece of dust carried a charge of plus 2.4 nanocoulombs moving to the space between the plates. Calculate the force on the dust particle. Then the mass of the dust particle is 4.2 micrograms. Calculate the acceleration of the particle towards the negative plate. And then a small sphere carries a charge of 2.4 times 10 to the minus 9 coulombs. Calculate the electrical field strength at a distance of 2 centimeters from the center of the sphere and 4 centimeters from the center of the sphere. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we're using the electrical field strength equation. Now, because it's between 2 parallel plates, it's a uniform field, so we can use the equation E is equal to V over D, where V is the potential difference and D is the separation of the 2 plates. Remember, we convert kilovolts into volts, so we convert centimeters into meters, so we get our answer out to be 6.25 times 10 to the 4 volts per meter. Now in this next question again, we can use the general equation now for the electrical field strength equation, which is E equals F over Q. So therefore F equals EQ. We've just worked out what E is in the previous question, the electrical field strength. Multiply it now by the charge. Remember, nanocoulombs must turn into coulombs, so you work it through to be 1.5 times 10 to the minus 4 newtons. Now again, you're given the mass here and has to work out the acceleration. Now because you've got a uniform field, it tells you you'll have a constant acceleration, so it can actually help and use the equation A equals F over M, or F equals ma. We've got our value for F from the previous question. We know it's 1.5 times 10 to the minus 4 divided by the mass. Now again, we turn micrograms into grams, but so it's 4.2 times 10 to the minus 6, so it's 3.6 times 10 to the 4 meters per second squared. In this next question, we now, because it's a sphere, have to use the radial field strength equation. So that is E equals Q over 4 pi epsilon 0 r squared. So you pop in all the values. Remember, it says 2 centimeters, but we don't work in centimeters in physics, we work in meters. So you've got to pop it through to be 0.02. Remember, it's r squared, so it's a squared value, so we get 5.4 times 10 to the 4 volts per meter. Now in this next one, you can work it through by either doing E equals Q over 4 pi epsilon 0 r squared, or you could say the relationship is E is directly proportional to 1 over r squared. So therefore if r is doubled from 2 to 4, well therefore E is going to quarter because it's proportional to 1 over r squared, so therefore you quarter the previous value and it's 1.4 times 10 to the 4 volts per meter. The next question says, the electrical field strength is constant close to a conductor. State the field pattern produced by the electrical field lines. Then below shows the field pattern correctly drawn by a student but with the charges on the sphere and the plate omitted. State the charges on the sphere and the plate, and then suggest how the field pattern below would change if the sphere shown below had a greater charge. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question you've got to understand what does a uniform field look like. So a uniform field will look like the lines being parallel and equally spaced, because the density of the field line shows the field strength. So if you've got a uniform field strength, you've got a uniform field line density. Now in this next one you can note that the arrows are pointing away from the sphere. Now the arrows point in the direction that a positive test charge would move in, so if they're pointing away from it, it must be getting repelled, so it must be from another positive charge. Now they're going towards the plate, so it must be attracted to the plate, so that will be a negative charge. Now again, how can we indicate what the field would look like? Well, it would still be radial because it's still going to actually be a sphere, but there would be more field lines at the sphere in that particular area because the density of the field line shows the strength of the field. The greater the charge, the stronger the field, the more field lines there are per centimetre squared. So the next question says, in a simple model of a hydrogen atom, an electron orbits a proton. The average distance between an electron and a proton in a hydrogen atom is 5.3 times 10 to the minus 11 meters. Firstly, calculate the electrical force on the electron at this distance. Secondly, state the electrical force on the proton. And thirdly, calculate the acceleration of the electron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question we need to work out the force, so we're using Coulomb's law. So F equals Q1 Q2 over 4 pi epsilon 0 r squared. We know the charge of the electron and the proton is given to you on the equation sheet, but you should memorize from the particles topic, 1.6 times 10 to the minus 19. You pop in all the values. Remember, we're squaring r, so we get 8.2 times 10 to the minus 8 newtons. Now this question is very interesting because it probes your understanding of what you're working out. Now in the Coulomb's law, you're working out the force on both of the charged objects. So both the electron and the proton have this 8.2 times 10 to the minus 8 newtons of force acting upon it. Then finally, we know the acceleration is F equals ma. So A equals F over m. So you do F, which you've just worked out, over the mass of the electron. Once again, it's given to you on the equation sheet, 9.11 times 10 to the minus 31 kilograms. So you get 9.0 times 10 to the 22 meters per second squared. The next question says, an alpha particle travelling through a partial vacuum is 1 centimeter from an electron. What force acts between them? Is it attractive or repulsive? Then two spheres with identical charges experience a repulsive force of 2.8 micronewtons when they are 12 centimeters apart. What is the value of this charge? So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we're trying to work out the force. Coulomb's law, F equals Q1 Q2 over 4 pi epsilon 0 r squared. You can then work through the values there. Now you'll actually notice that the values from the electron, so the charge there for one of them should be negative 1.6 times 10 to the minus 19. So you pop it through like that, you would actually get a minus 2.3 times 10 to the minus 24 newtons, so the force will be attractive. Again, here we're trying to work out the charge. Now it's important to know you've got two identical charges. So even though we know F equals Q1 Q2 over 4 pi epsilon 0 r squared, we can say Q1 Q2 are the same value, so therefore it's just Q squared. You can pop in all the numbers. Remember, 2.8 micronewtons becomes 2.8 times 10 to the minus 6. Remember, 12 centimeters becomes 0.12 meters. It's r squared. You pop it in, so you get our Q squared to be plus or minus 4.484 times 10 to the minus 18. Square root that, and we get plus or minus 2.12 times 10 to the minus 19 coulombs. It could be both positive or they could be both negative, okay, to get that repulsive force. The next question says, figure 23.22 shows a conducting sphere of a radius 0.80 centimeters carrying a charge of plus 6 times 10 to the minus 8 coulombs resting on a balance. Firstly, calculate the electrical field strength at the surface of the sphere. Then an identical sphere carrying a charge of minus 4.5 times 10 to the minus 8 coulombs is held so that at its centre it's 5 centimeters vertically above the centre of the first sphere. Calculate the electrical force between the two spheres, then calculate the new reading on the balance. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we're working out electrical field strength and it's on the sphere, so we've got to use the radial field strength equation. So E is going to equal to Q over 4 pi epsilon 0 r squared. Pop in all the values. Remember 0.80 centimeters becomes 0.8 times 10 to the minus 2 meters. Pop in all the values. You remember r squared, so you get 8.4 times 10 to the 6 volts per meter. Now we're trying to, in the second one, work out the electrical force. So we've got to use Coulomb's law. So we're going to say F equals Q1, Q2 over 4 pi epsilon 0. Pop in all the numbers. Again, now remember, 5 centimeters becomes 5 into meters, so it's 5 times 10 to the minus 2 meters. It's a squared value, so you work it through and you get 9.72 times 10 to the minus 3 newtons. Now it's also important to note what's the new reading on the balance. Well, you have the original reading is 0.0482, but now you've got this electrical force that is acting in the opposite direction to the force of gravity pushing down on the balance, so therefore you've got to subtract it from there, so you get 0.0384 newtons. The next question says, in a simple model of a hydrogen atom, an electron orbits a proton. The average distance between an electron and a proton in a hydrogen atom is 5.3 times 10 to the minus 11 meters. Firstly, calculate the electrical force on the electron at this distance. Secondly, state the electrical force on the proton. Third, calculate the acceleration in meters per second squared of the electron, and then show that the total energy of the electron is 13.6 eV. So pause the video now, then unpause the video and you want to go through your answer. Right, so we're working out the electrical force, so once again we're doing Coulomb's law. So we can say F equals Q1 Q2 over r squared, pop in all the values, remember it's r squared, pop it in there, 8.2 times 10 to the minus 8 newtons. That's the same force on both the electron and the proton as we discussed earlier, and we can say F equals ma, so A equals F over m. Once again you're given m on the equation sheet, so you can pop that through to be 9.0 times 10 to the 22 meters per second squared. Now, how to work out the total energy of the electron? Well, it's orbiting, and if you remember, we have the idea that in the total energy of an orbit, it's the kinetic energy plus that potential energy. We also know that the work done is going to be the charge times by the potential difference. So therefore, what we can say is that the energy is going to be equal to the kinetic energy, a half mv squared, minus E squared over 4 pi epsilon 0 r, because that's going to be our electrical potential energy, because it's going to be your field strength multiplied by another charge to work it through there. You can then rearrange that and you can work it all the way through, as you can see on the screen, until E equals minus E squared over 8 pi epsilon 0 r. Pop in all the values. Now remember, E in this context is actually the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs. Pop it all through and you get your answer out to be 2.2 times 10 to the minus 18 joules. You've also got to be aware of how to convert from joules into EV, and you can do that by dividing by the charge of one electron, which is 1.6 times 10 to the minus 19 coulombs. So you get our answer out to be 13.57 EV. The next question says, determine whether or not the electron initially at rest will reach point R shown in the diagram below. Both positive charges are 0.60 meters from R, and explain your reasoning. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this one through? Well, it's all about energies again. So you can work out your new potential energy when you're working through from these values. So you can say it's going to be 2 times by minus 5.76 times 10 to the minus 18 plus 2.88 times 10 to the minus 18. So therefore it's going to equal minus 8.64 times 10 to the minus 18 joules. So therefore when we work it backwards, because we can say that, well, potential is going to be this energy over charge. So we divide it then by the charge, charge of the electron, 1.6 times 10 to the minus 19, and we get our answer to be 54 volts. Now the potential energy has to be lower because the negative values are the same, but the positive is a smaller value. So therefore the new potential is higher than the original, but because the positive potentials are the same, but that negative potential is got smaller. It's gone from 36 volts to 54. So it can either travel to a lower potential energy, or it'll gain kinetic energy, or it'll travel to a higher potential because that electron is negative. The next question says, below shows two parallel plates 10 centimeters apart. So calculate the electrical field strength between the plates. The potential difference across the plates is 40 volts. And then you calculate the work done on an electron as it moves from plate A to plate B. And then an electron with a kinetic energy of 20 eV is injected into a field at point X. Describe and explain its motion in the space between A and B. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, electrical field strength is between two plates, so therefore it's a uniform field. We can use that uniform equation, E equals V over D, but remember we don't use centimeters, we use meters, so it's 40 over 0.01 meters, 400 volts per meter. Work done is going to be the charge times by the potential difference. You'll see the potential difference from the diagram is 40 volts, because we go from 0 to 40, multiplied by the charge of the electron, and we get 6.4 times 10 to the minus 18 joules. So the next question, well, you'll notice that the electron is going to be attracted by B, if you look on the picture, and it's going to be repelled by A. You can tell that because it's going to want to go to the positive charge, which is on the positively charged part of the plate, which is the 40 volts one, so it'll go towards the right. So what will happen is, as it's injected in, the electron will decelerate. It'll not go all the way to the 0 volts, to the A plate. What it'll do is it'll stop at the halfway point, okay, and then it'll return. The next question says, a maintenance engineer services power coating equipment that works on the principle of electrostatic attraction. The charges on two particles have been recorded. The force between the two particles is 8.2 times 10 to the minus 8 newtons. Calculate distance r between the two charged particles. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we're trying to work out a value when we've been given a force. So we can use Coulomb's law. So we can say F equals Q1, Q2 over 4 pi epsilon 0 r squared. We can therefore make R the subject, but it's going to be r squared. So you work out what r squared is going to be, popping in all the numbers. Now you're given the charges in the diagram, and you're given the distance in the and you're given the force in the question. So you get r squared to be 2.24 times 10 to the minus 15. Square root that to get your value of r, which is 4.7 times 10 to the minus 8 meters. The next question says, a student is investigating the electrical potential around a point charge Q. Point P is at a distance of 0.65 plus or minus 0.2 meters from Q as shown in the diagram. The potential at point P is 2.1 plus or minus 0.1 volts. Firstly, calculate the value of the point charge. Then secondly, calculate the absolute uncertainty in the point charge. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know what the potential is. We want to work out the charge. So the equation for potential is V is equal to Q over 4 pi epsilon 0 r. You're given that equation on your equation sheet. Rearrange that, make Q the subject, pop in the values, and we get our answer out to be 1.5 times 10 to the minus 10 coulombs. Now you'll notice for Q, it's going to work through to be V times by 4 pi epsilon 0 r. So that tells us we work out firstly the percentage uncertainty in R, which is 0.02 over 0.65. It's the absolute uncertainty divided by the value times by 100, so we get 3%. We do the same for the percentage uncertainty in the potential, which is 0.1 over 2.1 times by 100 is 4.8%. Because you're multiplying the two values in your equation for Q, you'll add the two percentage uncertainty, so that gets you 7.8%. So therefore you work out 7.8% of the answer, which is 1.5 times 10 to the minus 10. So you get 1.17 times 10 to the minus 11 coulombs. The next question says protons are accelerated by an electrical field between the metal plates A and B in a vacuum. Part of the apparatus used is shown. Firstly, explain why the protons are accelerated by the electrical field. Then a proton is travelling at a speed of 3.8 times 10 to the 5 meters per second at plate A. Show that the kinetic energy of the proton at plate A is 1.2 times 10 to the minus 16 joules. The potential difference between plates A and B is 2.8 kilovolts. Calculate the work done on the proton as it accelerates from plate A to plate B. Then determine the speed of the proton at plate B. Then the distance between A and B is now doubled. The potential difference between A and B is unchanged. Another proton with the same initial speed at plate A is accelerated between the plates. State what effect, if any, this has on the speed of the proton at plate B. You must justify your answer. So pause the video now, then unpause the video when you want to go through your answers. Right, so why is it accelerated? Well, the protons are positively charged, so therefore, because they're charged, they'll experience a force in an electrical field, that's the definition of a field, that will cause acceleration. The kinetic energy, it's a half mv squared, so it's a half times by the mass of the proton given to you on the equation sheet, multiplied by its speed squared, pop it all through, and you get 1.2 times 10 to the minus 16 joules. Then this next question, the work done, is going to be the charge times by the potential difference. So you've got your charge of your proton, you know that, it's given to you on the equation sheet, 1.6 times 10 to the 19, times by the potential difference, 2.8 times 10 to the 3, because we don't work in kilars, we just work in volts. So therefore you get 4.5 times 10 to the minus 16 joules. So how can you work out the speed? Well, we know that the kinetic energy is going to be the initial kinetic energy, which you worked out in the second part, plus this work done, because work is being done on the object as it's accelerated in the plates, in between the plates, sorry, when it's in the field. So now we've got a new kinetic energy, and then we can say it equals a half mv squared. So we know what that value is, we know the mass, we want to work out the velocity, so we rearrange it, we make v the subject, and we get 8.3 times 10 to the 5 meters per second. Now what effect will this have on the speed of the proton? It'll have no effect, because the work done on the proton is the same, because the distance is not a factor in how much work is done. And if it's another proton that goes in at the same initial speed, it'll have its same start and kinetic energy. So therefore the only work done on it is q times by v. It has the same charge, it has the same potential difference of the plates between it, so therefore the work done is the same. The next question says, firstly, define what is meant by the electrical field strength at a point. Then in a particle accelerator, a proton initially at rest is accelerated between two metal plates as shown in the diagram below. Firstly, calculate the force on the proton due to the electrical field. Then calculate the work done on the proton by the electrical field when it moves from plate A to plate B. Then state the energy gained by the proton, and then assuming that all this energy is converted to kinetic energy of the proton, calculate the speed of the proton when it reaches plate B. So pause the video now, then unpause the video when you want to go through your answer. Right, definition of electrical field strength, you've just got to learn it. It is the force per unit positive charge. Remember, we always define electrical field strength quantities in terms of test positive charges. Everything is done in terms of positive charges. The force will be equal to EQ, the electrical field strength, times by the charge. So, but first we've got to work out what the electrical field strength is. Now it's between two metal plates, that tells you it's a uniform field, so we can use that uniform field strength equation of E equals V over D. So we can pop in all the values, we got those from the diagram, so you can work that through, multiply them by the charge to work out the force to be 1 times 10 to the minus 11 newtons. Work done, we've just done this before, work done is going to be F times by it's going to be times by the displacement. That's an equation you've looked at when you've done mechanics. So work done is going to be force times by displacement in the direction of the resultant force it acts in. So you've got that force, you know the distance it's moved there, so the work done is 8 times 10 to the minus 13 joules. That's the work done on the proton, so that's how much energy is gained by the proton, because work done means either energy gained by the object or lost by the object. And then to work out the speed, you can say kinetic energy is a half mv squared. Okay, you know the work done is 8 times 10 to the minus 13, which in this instance is the kinetic energy gain. So you can work out V. You know the mass of the proton before, because it's given to you in the equation sheet. You pop it all through and you get 3.1 times 10 to the 7 meters per second. So that brings the end to our revision session today. So hopefully in this revision session you've looked at how to answer A-level physics examination style questions. You can assess your understanding on A-level physics and understand what topics you need to improve upon for A-level physics for the electrical fields module. So thanks so much everyone to listen to this revision session on electrical fields for the AQA A-level physics paper 2. Thank you so much and have a lovely evening.